Hello, welcome back. This is lecture 3. So in lecture 1 and lecture 2, we talk about the lattice and also lattice vibration. All right, and then we introduce a few important concepts such as reciprocal lattice, Brillouin zone, and then phono. All right. So in lecture 1 and lecture 2, we didn't touch on electrons. From lecture 3 onwards, we'll focus more on electronic properties of semiconductors. So basically, we need to understand how electrons behave in different type of materials. To this end, we need the concept of quantum mechanics. Since not all of you have studied quantum mechanics before, I will just give you a brief introduction on what quantum mechanics is first, before we move on to talk about semiconductors. Okay, in classical physics, when we talk about the moment of an object or particle, for example, electron in free space, we need to so basically know a few things about electrons, right? So the first, when you know where the electron is, so basically it's a physical location, and then to do this, and then we need to introduce a reference system. For example, we have this XYZ coordinate system here, and so once we have this reference system, and then we can specify the location of electrons, right? Say for example, given by position vector r, right? And then once we know where it is, and we still want to know whether it's stationary or it's moving. So once it's moving, and then we want to know what's the velocity, and then also want to know how this velocity will change with respect to time. So that basically is acceleration, right? So once we know r, v, and a at any instant of time, and then we should be able to quantify the movement of electrons in free space, right? And so you know that these three parameters are related to each other. So from a Newton's second law, we know that the mass of electrons multiplied by acceleration, which is second order derivative of r with respect to time, and this is equal to the net force acting on this electron, right? And so, of course, if we integrate these ones, and then we should be able to find velocity. So that basically, so velocity is equal to, the integration that basically is f divided by m, and then you integrate this with respect to time, right? And so this basically will give you the velocity. So once you know velocity, and then we can integrate further, and then we should be able to get the position, all right? And of course, to get specific position, the specific velocity, and then we need the so-called initial condition. So at the t equals 0, and then if you know that, so v is a v naught, and then r is a r naught, and then you should be able to solve this second order differential equation, right? And then combine the two together, and then you should be able to find out r, v, and a, right? In quantum mechanics, the concept is totally different. In quantum mechanics, we cannot specify where the particle is, but we can always try to find out what's the probability for you to find the electron at a certain position in space at any instant of time, all right? So in this module, so we will only focus on stationary case or steady state case. So this means that we'll ignore time dependence we only focus on the position dependence of variables which we use to describe the electron's behavior in semiconductors. All right. So to specify the probability of electron at any fixed location in space, we need to introduce a concept we call wave function, which is very, very important. So we call a wave function. And so typically we use a psi to specify this. And then psi is a function of a spatial variable r. And of course, in three-dimensional case, r basically is a vector, right, specified by the three coordinates x, y, z, all right? And the probability for you to find this electron at a position r is given by psi complex conjugate, all right, and the r, and then psi. Okay, and so of course you can see that this is a function of r, right? So in general, psi is a complex function. So, but if you multiply it by its own complex conjugate, you get a real function, right? So this means that it's something which is measurable. Okay. Now, since this is a probability distribution of electrons in space, and then if you integrate this for the entire space, and then we should be able to specify, sorry, not specify, okay? And then if we integrate this in the entire space, and then this should give you unity, right? It's one, because the probability for you to find the electron at a certain physical location is not one. But if you try to find the electron in the entire space, and then if you sum all this probability together, it should be one, right? So that's why I just integrate this, and then so this be one, okay? And of course, so dV is a small volume in space, so it's given by dx and dy dz. So you just need to do this triple integral, right? And then you should be able to find out that, so if this wave function, this is called normalization. This means that if this wave function is normalized, and then if you integrate the product of this wave function with its own complex conjugate, and then you should be able to get one. Okay. So now, so this means that in principle, if you can specify, you can find out this wave function, all right? And then you should be able to find out the distribution of electrons in space, right? Although you cannot specify the electron at a certain location, okay? And so, and then from this wave function, and then we can also calculate the electron energy, right? Which is very important. Okay, so now, and then what exactly is this wave function? Okay, to understand this, let's look at okay, let's go back to this the screen again. Okay, just remember that when we try to specify the position of a particle in classical physics, right? So you have in the 3D coordinate system, we have x, y, z. Okay, so now if the particle is here, and then remember how do you specify this? And of course, we just specify this as so r, okay, equals and x I. So I basically is a unit vector along x-axis in the yj, and j is unit vector along z-axis, right? So basically we have I, j, and then k here. That's what we do, all right? And then, and so x, y, z are basically the projection of this vector onto x, y, and the z axis, right? And then you put these three together, right? And then by combining the three scalars with these three unit vectors, and then you can find out the location of this, right? But the problem is, why do you need to use this kind of coordinate system? It's not necessary, right? You know that you can use a spherical coordinate system, right? And then cylindrical coordinate system as well, right? For example, if it's in spherical coordinate system, so one, and then what happens that if you understand this, if you have learned this before, well, so if we draw this spherical coordinate system in XYZ coordinate system, so for example, for any point here, so how do we specify this position for the same position? So of course you have R here, that's a vector, right? And then we have something we call this angle, we call theta, and then we project this one down to XY plane, and then we get this projection, and then this angle we call phi. Okay, so if we know this, and then the same location, we can specify this one as, and so of course now you don't use IJK, right? So what we know that we use basically, and R. Okay, so R, and then so basically unit vector in R direction, and then another unit vector which is theta direction, and then one more unit vector which is in phi direction. All right. So and then so basically you can write this one as so R, which is for example the magnitude of this. All right, and then you have a unit vector which is in R direction. Okay, and then you can have a phi which is the angle. So that phi basically is an angle, right? You can see this is phi. And then you can use a unit vector which is perpendicular to phi axis, or sorry, along a phi direction. And then there's another one which you call it theta. Right? You can do that. But the problem that we're not so-called familiar with this kind of coordinate system, right? So that's why normally what we do that we don't do this. We still try to go back to our XYZ coordinate system, but we can convert this one into, say, for example, so now X will be R. So basically the length of this vector, right? So this R. Then we have sine theta, cosine phi. Okay, so we do this, and then again we go back to our this unit. This IJK, the three unit vectors, right? And then we have this R, and then sine theta, and then cosine phi. So we have J. Then we have this R, okay, and then cosine theta, and then we have K, right? So now you see what's the difference. So now, by right, if you choose this kind of coordinate system, you should have this very simple expression, right? And then for XYZ, we know that basically this one. And however, since we are not familiar with this kind of system, so that's the reason why we always convert this into this XYZ coordinate system. And then so that, you see now, these are written to this one. Okay, so this means that if you, the position itself in the XYZ coordinate system, this point itself, if you call it P, so this is basically physically is the same point in real space, right? However, mathematically, you can have a different way to express this, depending on what kind of reference system or coordinate system you choose, right? If you choose a different coordinate system, and then mathematically, the way which you can specify this physical position is different, but physically that's the same, right? So now, if we try to generate this into the quantum mechanics, so what this, and actually quantum mechanics is very simple. So what this, so let's move on to next, change the screen again. So in quantum mechanics, we don't use XYZ coordinate system per se or spherical coordinate system, right? It's not necessary. We can introduce another very abstract coordinate system. So what this? So just imagine that so each coordinate, the coordinate axis is not necessary to be a straight line. So it can be, something like this one, right? So This basically is a function, right? It's not necessary to be a straight line, okay? So this is our coordinate system. And then, so each coordinate axis, so we just call wave function. So we call phi1 and then phi2, right? And then, so just phi I, just continue, okay? And then you have an infinite number, this kind of wave functions. So each of them, just try to realize that this indicate just one coordinate axis, right? And then for any point in real space, so this point P, okay? And then this point P, I can just use this one to indicate, because now this is not in real space. This is in a very abstract space. And then the state of electron. So just now in the classical physics or in classical way, if you want to specify the position of a particle, you use the position vector R, right? So R can be represented in different ways in different coordinate systems. So now, so in quantum mechanics, we don't specify the physical position of electron. So what do we specify? We specify the state. So we call the state of electron, right? The state of electron. So this state of electron is given by psi. This is the wave function we just talked about, right? And then, so this wave function can be written as the linear combination. So I from C1 to infinity, and then Ci, and then phi I. Okay, so if we can find out a suitable phi I, this means we have infinite number of this, right? So if we can, this is called basis. If we can find a suitable basis, and then we should be able to express the state of electron in this very simple way, right? So Ci basically is a complex constant, it's a coefficient. So this is exactly equivalent to in classic case, for example, the position vector. So now we said that this is given by xi plus yj plus zk, right? We can also write this one into this form. So we see I from 1 to 3, then we call Ci. So this ijk, we just call unit vector, for example, we call alpha, right? So so alpha 1, so then we have alpha 1, this unit vector basically is I, and then alpha 2 is j, and then alpha 3 is k. So now you can see that, so this I, j, k are basically the basis, right? So once you have this base function, you can call it, anyway, you can call it a very simple function, right? And then any physical location in real space is just a combination of all these so-called base function. So here is a unit vector, right? With a different coefficient, right? And then of course, in this case, your C1 is X, and then C2 is Y, and then CZ is Z. Sorry, this is C3, right? Now, then you may see that, okay, with that simple, then we should be able to choose any IJK we want. You're right. You can choose any IJK you want, but there is a condition. So what is condition? The condition is that is alpha I, okay, dot with alpha G is given by, okay, delta IJ. So this is called orthogonality. So what does this mean? This means that, for example, if alpha I and alpha J are the same, this means that, for example, you have I dot I, so you can explain this one. This means that I dot I is 1 because they're the same. This is alpha 1 dot alpha 1. But I dot J, so they are 0 because this alpha 1 dot alpha 2, right? And then, but the J dot J is 1, right? Just continue. Okay, you have a few other, combinations, all right? So this is in this is a classical way to specify a single point in real space. And in quantum mechanics, it's the same thing. So now we only need to require this. We require this Ci, okay, and then Cj to be equal to delta Ij. So what does this mean? This means that when I and j are the same, and then this is 1, and then if they're not the same, and then this will be 0. This is called orthogonality. But now you look at this dot product, and then this is called inner product. So what's the difference? The difference that so this is just a simple dot product between two vectors, right? But this is different. What does this mean? It means that you integrate this phi I and then phi j complex conjugate. Okay, so it can be opposite way anyway. So and they integrate in the entire space. So this is given by delta Ij. So this means that these two wave functions, fi and the phi I and phi j, and the inner product of these two should be 1 if they're the same, and it should be 0 if they're different. It's very similar to this the orthogonality of the unit vectors. And then for the unit vector case, we only, for a 3-dimensional system, we only have 3 unit vectors. And then we don't call, normally we don't call orthogonality, but we call that they're perpendicular to each other, right? Because they're straight lines. But in quantum mechanics, and then we have a very abstract coordinate system. And then we have an infinite number of coordinate axes. And then each x basically is a wave function phi I or phi j. Okay, and then so those so-called basis functions or wave functions, they are also orthogonal to each other. So once we can find out this kind of a basis, and then any electron state, all right, can be expressed, or the wave function of this electron at any state can be expressed as a linear combination of this basic wave functions, right? So in other words, in quantum mechanics, what we are trying to do, we are trying to find a space, a coordinate system, right? So this coordinate system will simplify the expression of the wave function of electrons, right? So, so if we go further, then so this is a picture you should have. So the state of an electron at any point in space is given by a wave function phi. And then this wave function phi, and then we choose this kind of a coordinate system. So we basically, we have an infinite number of phi, right? And then once we choose this, and then we have this cosine r, which is equal to the linear combination and of this phi I, all right? So this is what we have. And of course, this phi itself is a wave function. That's why it's a prediction of r as well, okay? So now, remember this, just single r itself if you want. And then, of course, so this basically in x, y, z coordinate system, all right? And then your phi I, since it's a function of r, of course, you can express this one in this coordinate system, right? And so what it is, this phi I r general is a field, scalar field, and of course, a complex function in x, y, z coordinate system. Why? Because at each point, so phi I has a specified value. In general, it's a complex function, okay? And then you move on to this, then you can see that so each state of this can be expressed as a combination of this phi I. So this means that in principle, if you don't want this, okay, and then you can directly express this one in this XYZ coordinate system, right? But this is very complex. So it means that it's almost unhandleable, right? So that's why it's very complex. That's why it's very difficult. However, if you introduce this is something like an intermediate abstract space, and then you can see that it becomes so simple, just like this, just a linear combination of this, right? And then this is very similar to, as I explained, just one point in XYZ coordinate system, and then this can be written as something like this one, right? So only from 1 to 3, and then you have so you just now use CI if you want to use the CI, and then alpha I, which is the unit vector, right? You can see that a single point in XYZ coordinate system you can express very easily because this is what we have been used to this, right? And then, however, for quantum mechanics, if you express wave function directly in this kind of coordinate system, it becomes very complicated, right? So that's the reason why we introduce another coordinate system we call abstract coordinate system, which is defined by phi I. So once we do this, and then you can see now, so this becomes very simple. That's the basic idea, all right? So nothing is wrong with this, right? That's basically, we see that the mathematics is extremely important because mathematics can help you to do abstraction, right? Can help you to choose a proper coordinate system so that you can easily describe this electron behavior in a quantum mechanical way, right? So I hope you can get some idea about this, okay? So now the next question is, how do we find out this phi I? Okay, so how do we find out this phi I? Then let's go back again. Remember, how do we find out R? I already explained. So that basically is from this Newton's second law, right? This is a very important equation, and that's for classical physics, right? And then how to find out, since we know this cosine, right? So cosine in quantum mechanics is given by the linear combination of phi I, right? And then, so how to find out this phi I, okay? So do this, we don't use Newton's second law. We use another very important equation we call Schrodinger equation. So what this? We have something called Hamiltonian, and then multiply by, so this wave function, right? So multiply by this wave function. And then this wave function, if you can find, if you can find a proper coordinate system, and such that this h phi is equal to a constant multiplied by this wave function itself, and then so this phi will have many solutions. Okay, the phi many solutions. So you have phi 1 and the phi 2 and the phi 3. Sorry, phi I. All right, and then corresponding to each of these, and then you have a different coefficient E1, and then E2, and then EI. Okay, so if you can find this kind of a solution, and then this phi 1, phi 1, phi 2, and phi. So these are basically will be the basis of your coordinate system in quantum mechanics, right? We'll call wave function. And then E1, E2, EI will be the energy of electron at that state, okay? And then any other state will be the combination. Any other state will be combination of this. So this means that, these solutions are basically, we call some sort of equilibrium state. This means that at the equilibrium state, so this electron, okay, is possible for this electron to occupy any of these energy levels with a certain probability, okay? And then if you apply driving force and how this state will change. So this means that the state, how it will change. And then this basically is so-called time dependent. So Schrodinger equation, which we will not deal with. So we only deal with this kind of stationary case, right? So now, what's this a Hamiltonian. So the Hamiltonian for any particle, this can be written as two parts. So one is called kinetic energy part. The other one is related to potential energy. But this Hamiltonian is an operator. It's not a normal function. It's operator. So it will operate on another function. For example, here this is phi. So what this, and this is given by, in general, you can calculate from momentum operator divided by 2m, and then plus potential energy operator. Okay, so this momentum operator P. So this operator, sorry, it's not P. So this P is given by h, which is a Planck constant, divided by I, and then del. So del is operator. So it can be written as, in a 3D coordinate system, partial x, and then partial y, and then partial z. Okay, and then v itself, v is operator, but v itself basically is a v. So for example, if you can find out potential energy as a function of r, and then so your Hamiltonian basically will have the same form as your potential energy, right? And so now if you square this, and then you get this one, so minus h squared, all right? And then so you have a partial x, right? Square, then plus partial y square, and then plus square partial z square, right? Again, this is a operator. Then you just need to substitute this one here, right? And then you get h, and then substitute h here, and then you get a second order differential equation with respect to x, y, and z. And then you solve it. If you find a solution which can satisfy this equation, and then you find the phi 1, phi 2, and then all this so-called based wave function, right? And then of course, and then you find the energy at all these different states as well. Okay, so as I said, at the stationary state, and then you have an electron has a probability to occupy all these different states. And so once you have a driving force, then you apply electric field or magnetic field or any other driving force, and then of course the electron will change state. But when this driving force is very small, the moment is very small. So in principle, as a first order approximation, and then the new state basically is a new wave function, and can be obtained from this in nature so-called steady state or equilibrium state wave function, right? So basically, what you see here that once you find this abstract coordinate system, right, and then you should be able to describe how electrons behave quantum mechanically, right? So these are some basic concepts which we will use in the next few slides. So I hope you get an idea about what quantum mechanics do in a very simple way, right? And of course, this might not be the very precise explanation of quantum mechanics, but for engineering students, I think this is good enough, and so that roughly understand why we use quantum mechanics and what quantum mechanics can do, and how it will help you to understand electron behavior in solid state materials. Okay, with this, let's come back to today's lecture. Okay, well, our ultimate goal is to understand how electrons behave in the semiconductors. So basically, it's in the real material. But to do this, we need to start from a very simple situation first, and then gradually just move on to the real case, right? So the simplest quantum mechanical system basically is the atom, right? And then among all these different type of atoms, of course, hydrogen is the simplest atom, right? So you know that inside the atom, so you have a nucleus, which is a positive charge. And then you have a different number of electrons, depending on what kind of atom you have, number of electrons which are moving around this nucleus, right? So at equilibrium state, so these electrons are tightly bonded to the nucleus due to a strong Coulomb interaction. And so, however, if you excite all these atoms by providing additional energy to the electrons, and some of the electrons will be able to escape from this Coulomb interaction, and then they'll become freely movable, electrons, right? And of course, later we know that in solid state material, and even you don't don't excite the atoms by providing additional energy from external sources, and then the interaction between all these atoms can also make electrons movable in some materials, for example, in metals, right, which we'll talk about later. Okay, so now if you come back to this single atom picture, so just now we explained that the behavior of electrons at a steady state or equilibrium state basically can be described by this Schrodinger equation. And then so in Schrodinger equation, on the left-hand side, you have this Hamiltonian. Then so if you use Hamiltonian to act on the wave function, and then if this it will generate new wave function. If that new wave function is a product of a scalar constant multiplied by the original wave function, and then that proportional coefficient basically is the energy, right? And then the wave function, which is satisfied the solution, basically are the basis functions, or what you call basis wave functions, right? And each basis wave function represents a certain mode of a moment of electrons in the single atom case, and then basically find out that the orbitals of electrons cannot be continuous in quantum mechanics, right? And also electrons inside atom will also take different energies. So it means that both energy and orbitals will be quantized. That's quantum mechanical picture. Okay. And then once we have this single atom in the picture, and then we'll move on to this simpler cases. Means that after we release electrons to a vacuum, and then we try to confine electrons again by some sort of electrostatic potential, and then you will see how the electron behavior will change, right? And then from there, and then we gradually move on to real material. So in real material, of course, we have a electrostatic potential formed by all the electrons from all the atoms. But the key point is that this electrostatic potential is periodical. So this periodical static potential will have a profound impact on the electron moment inside the material, and eventually it will give you a metal, semiconductor, and an insulator. This means that for some materials, inside these materials, the electron can move relatively freely, and then in other materials, electron cannot move, right? So this is what we'll explain in these two lectures, lecture 3 and lecture 4. Okay, so now we look at the first quantum mechanics system that basically called hydrogen atom. So the hydrogen atom has a special significance in quantum mechanics. This is the first system which quantum mechanics actually provides a very reasonable explanation. This means that for many of the experimental observations, we can use this quantum mechanics to describe it, right, inside this hydrogen atom. And of course, with this hydrogen atom, and we can also extend the same concept to electrons, to atoms with multiple electrons, right? But this hydrogen atom is especially useful or important for studying semiconductor physics. That's because that later you know in semiconductors, and actually for pure semiconductor, and the electrons cannot move, they cannot move around. And however, if you replace some of the atoms of the semiconductor by other atoms with different number of valence electrons. And what happens is that you create additional charge, which can be additional electron or is the electron vacancy, which we later know that we call hole. And so, but anyway, so this, for example, if you have a host crystal, which is silicon, and so this is a very important type of semiconductor. We're not going to detail anyway. Later, I'll talk about all this kind of thing. But anyway, and so at this moment, just know that in this kind of semiconductor, if you replace, for example, silicon by phosphorus, and then it has additional valence electron, and then you get one extra electron, which is loosely bonded to the nucleus of the impurity atom. And then this situation is very similar to a hydrogen atom, but it's different. Although it's different. However, we can use the same quantum mechanics concept, right, to find out the binding energy of this extra electron. This means that how easy is this electron? How easy is the electron? Is this electron be able to become a free carrier, right? So, so that's why this single hydrogen atom concept is quite important. Okay, and all right. But anyway, so this is a model for hydrogen atom. You can see that this is the nucleus, and then you have a single electron which is moving around this nucleus, right? So of course, the nucleus you have a proton and a neutron, right? And then so this in quantum mechanics, you know that this electron orbitals actually is discrete, and then at each orbital, and then you have a different energy, right, for the electron. Okay, and so to solve this hydrogen atom in quantum mechanics, and then we just need to rely on this Schrödinger equation, which we just talked about. So you can see that so cosine is a wave function, which we need to find out. So once we know the wave function, and then we know how to calculate the probability of this electron distributed in the free space, right? We don't know where it is, but we can find out it's a distribution of probability, which basically is given by probability density is given by cosine multiplied by applied cosine complex conjugate, right? So that's why the first step is always to find the wave function, and then this is a Schrödinger equation. So now, so you can see that so the one inside this bracket, so this is the Hamiltonian H, right? And then so this E is the energy, right? So if we can find the solution of this Schrödinger equation, and then we should be able to find out the both wave function and then also the energy associated with the wave function. And so this mu is a reduced mass. So mu reduced mass is defined as so 1 over mu is given by so 1 over so me. So me is an electron, and then plus 1 over m. So m is the mass of a nucleus, right? So since the mass of nucleus is much larger than the mass of electron, so in principle, so mu is roughly equal to the electron mass. Okay, so we call reduced mass. And then h is a Planck constant. Or del square is a del square operator, which I just already talked about. And then so this part is due to the potential energy. So here we call potential energy operator, but you can see that basically the same as a potential energy, right? So due to Coulomb interaction. Okay. Now, of course, you can try to solve this one in XYZ coordinate system, but it's going to be very complicated. So since this hydrogen atom has a spherical symmetry, so this means that electron inside the hydrogen atom will feel electrostatic potential of a spherical symmetry. So in this case, it's always good to solve this in a spherical coordinate system. So in spherical coordinate system, so you know in XYZ coordinate system, so this so del square is given by partial r square, partial square partial x squared, and then partial square, partial y squared, and then partial square, partial z squared. So this is in XYZ coordinate system. And however, in spherical coordinate system, so basically it's given by this, right? So we have this three variables specify a certain position in space. That is r, theta, and phi. I already explained when I use a whiteboard, right? So now, and this is a standard textbook problem. So we will not try to solve this, but if you have solved this a long time ago, and if you are interested in this one, and or you have not learned this before, you can always try to look at the quantum mechanics textbook, right? So this wave function, and so can be write into three parts. So this basically called, sorry, two parts. So this is called separation of variable method. All right, it's the standard method we use to solve second-order differential equations in physics and engineering. So we have one part which is dependent on the position variable r, and the other part is dependent on theta and phi. Okay, so we substitute this del square and also this wave function into a Schrodinger equation, and then we solve it, and then people find that and so energy becomes quantized, right? So basically you can see that, so this E, and it's basically this E, right? So, and so basically people find that many phi, not just one single phi, which satisfy this equation. And then each phi is corresponding to a different proportional coefficient here, and then this basically is energy, right? So why this is energy? And that's because if you look at the Hamiltonian itself, has a dimension of energy, because this is a potential energy. This is a kinetic energy, right? So although both are operators, but they still have a dimension of energy. Since the phi is the same, so if this h and the dimension has a dimension of energy, and of course E also has a dimension of energy, right? So then people find out that E is not just a single value. And that's because the phi can have different functions, and then all these satisfy the same equation. So for example, for phi n, and then people find out that so the n actually is used here as the index, right? So these are the special functions. If you're interested in this one, and then you can go back and look at quantum mechanics textbook. So this wave function, when n is different, they are different. Okay, so because this part is different. So now, and then people find that basically this En can be written like this. So these are just a prefactor that are constant, right? So epsilon not basically is a vacuum dielectric constant, right? And then this E is electron charge, right? And then A naught is given here. It's called Bohr radius, okay, and it's 0.529 angstrom. So this anyway, this already solved by quantum mechanics, so we don't need to go to details. But anyway, this is just a real number, right? Has a dimension of length, and then n is an integer from 1 onwards. Okay, so now since all these are constants, so we can calculate. So actually, this is a 13.6 eV and the 1 over n squared. Okay, so now obviously, and n is different, and then this energy will be different, right? And so in addition to this, so obviously energy is not continuous because n is integer, n is not continuous, right? So now the one important factor you had to notice that, so there's a negative sign in front of this, right? So what does this mean? This means that you can see, look at what happens when r approaches infinity. Okay? So when r approaches infinity, so basically you can see that this potential energy is 0. So this minus sign basically means that when you use infinity far away as a reference, okay, this means that when electron is in far away, and then the energy actually is 0. So this means that okay, this means this is the nucleus, which is here, right? So if you put electron infinity far away, say for example, this is infinity far away, and then this energy should be 0. And then when you burn this electron, okay, all the way to here, right? And then the work you have done basically is a minus 13.6 eV. So what does this mean? This means that the electron now is bonded to the nucleus by this amount of energy. Okay, or in other words, if you want to move this electron, to make this electron escape from this the first orbital. Okay, so this is the second one, the first orbital, to infinite far away the place or location. This means that basically it's to make electron, to free electrons from the interaction from the attraction from nucleus. The energy it provides is minus 13.6 eV. So this is called ionization energy. So this means that electron inside the hydrogen atom is tightly bonded to the nucleus. If you want to release this, and then you need to provide energy of 13.6 eV, right? That's the minimum energy which you need to provide. And of course, you don't need to excite electron to just by one step, okay, to infinite far away. And then you can also excite it's called excitation state. For example, if you move this, excite this electron from n equals 1 to n equals 2 state, and then the energy you need to provide basically the difference between the two, right? Okay. Now, this quantization of energy is extremely important. And why this is important? So basically, this is where you get light from. Okay. So a light, of course, is an electromagnetic wave, right? But in quantum mechanics, so this electromagnetic wave can also be described by photon. We call it photon, right? And then, of course, photon has an energy. Okay. So the light is generated by the recombination of electrons between two energy levels. So, for example, at ground state or so-called equilibrium state, if you have electron which occupies lower energies, typically we call it, for example, ground state, right? And so if you excite this, you can excite this electron to an excitation state, right? Just one state above this. Okay. So of course, and you can use light to excite this, or you can use any other external energy source to excite electron to the excitation state. But the electron at the excitation state is unstable, right? So it always tries to jump back to the lower energy state, or in this case, the ground state. And then during this process, and of course, you can convert this energy to a different form of energies. So for example, you can convert this into heat, right? But if you have a right environment or right material, and then it may also convert this into electromagnetic energy. So that basically is a light. So this is called a radiative recombination, right? And the energy of this photon emitted during this recombination process basically is equal to the difference between the energy at these two levels. So of course, the energy of photon, if you studied physics before, it will determine the color of the light, all right? And so, okay, so in this case, if you don't provide any additional means to control this recombination process, this means that you let this electron jump back spontaneously, and then we call spontaneous emission, and you get something called normal light. So what does this mean? That you may have many electrons, not just one, right, at the excitation state. And then when they jump back, the phase is different. So eventually get light, but the phase is not the same, right? And however, if you provide any additional mechanism, typically called feedback, and then you can ensure that all these electrons will jump back together with the same phase. So that's called laser, right? It's a different type of light. It's called coherent light, okay? And then you will learn this in the second part. So now, how is this color of the light related to the energy of the photon? And then we have this very simple relationship, which is shown here. So we have the energy of the photon, right? And then we have the wavelength of the light, and then we have frequency, right? So of course, light with different wavelengths have different color. So you can see that energy and the frequency are related by this very simple way for photon, right? They are proportional to each other. So the higher the frequency, the higher the energy, or the higher energy, the higher the frequency, right? The difference is just a Planck constant, right? And then the frequency and the wavelength, of course, related by this equation, and the c is the speed of light, right? Which is a fixed constant. So this means that once you know the frequency, and then you know the wavelength, and then so this means that wavelength is already to energy. And in semiconductor physics, that's a very simple equation, and then we use very frequently. That's basically energy in EV is related to wavelength in micron by this very simple equation, right? So for example, if lambda is 1 micron and then wavelength is 1.24 EV, so this basically is in the infrared range, right? So if lambda is 0.5, which is the current light, 0.5 micron, and then this energy is 2.48, right? 2.48. So basically, for example, you have a and so 1.24, right here, right? So 1.24 milli electron volt. So 1.24 EV is 1 micron, right? And the corresponding frequency is 300 terahertz, all right? And so, and of course, the visible light somewhere here is a very, very narrow range. Now, for example, for a hydrogen atom, this means that if electron can really jump from say free state to in this ground state of hydrogen, and then that energy difference is 13 point something, 13 EV, right? Of course, normally that will not happen. But if you really that happen, you see what the wavelength. The wavelength will be 13.6 somewhere here, right? You can see that is basically is in the deep extreme UV, right? That kind of range. Okay, and of course, you move on further, and then you have this X-ray, right? This X-ray range, and of course, wavelengths become smaller, right? So visible light typically is 0.4, around 0.4. 0.4 is already near UV, okay? 0.4 to 0.8. So 0.8 micron is near infrared. So we already cannot see it, okay? So that basically is about a photon and how the photon energy is related to wavelength and also frequency. Okay, so now I'll come back to this hydrogen atom. So now you know that so the electron is tightly bonded to the nucleus in the hydrogen atom, right? So this means that in the isolated atoms or neutral hydrogen atoms, and you do have electrons, but we cannot make use of this for electric conduction, right? And then for electric conduction, it means that they release electrons. So once you release electrons to vacuum, and then if you can find a way to control this, and then of course, and then you can form electronic devices. So that basically is called vacuum electronics, like vacuum tubes. So all this kind of very bulky devices. But to do this, you can see that you need to supply a very high energy, which is not practical for real applications, right? So that's why the best way to release these electrons and from the nucleus, this means make electrons and make electrons move freely, and that actually is in solid state materials. So this means that so this is a vacuum case we already explained, right? So if you can release electrons in a vacuum, and if you can control it, and they can form a device. But the problem for this kind of device is that the carrier density is very low. So it means the number of electrons you have per unit volume in vacuum is very low. And of course, to control it is not so difficult. You just need to apply electric field, right? And they can control it. And then of course, you can make a device, okay? But it's very difficult to make a small device. So this means that this kind of vacuum electronics, vacuum tubes, for example, I mean, in some high power applications, people are still using these kind of devices, but it's very difficult to form a large scale integrated device. So that's the reason why people have tried to find, solid state materials. So in solid state materials, you have many atoms, right? So with them, we talk about the lattice structure of semiconductors. So basically, you have a periodical arrangement of atoms inside the semiconductors, right? So, and then in this, once you can form a lattice, so this means that, or also put in this way, the fact that you can form a lattice means that there are interactions among the electrons, right, from different or neighboring atoms. And depending on what kind of atom you have, and then what's the atomic spacing, and how these electrons will interact with each other. And then for some materials, and then we have something we call metal, for example, copper, and then gold and silver. These are very good conductors. So in this kind of materials, and somehow due to this, the interaction of electrons from neighboring atoms, and then some of the electrons will become free to move inside this material, right? And then you get a very good conductivity. This is something called metal, right? And then for another type of material, and so they interact with each other, but they form some sort of relatively strong atomic bond. And then, so basically neighboring atoms, they share electrons, but the electrons are not so easy to move freely. And in fact, at low temperature, they cannot move freely, right? And however, this kind of bond typically is not as strong as inter-atom bonding, just like a hydrogen atom, right? And so that's why if you just supply a reasonable amount of energy, externally, and then you should be able to excite these electrons to a higher energy state, which I mean, electrons at this kind of states are relatively easy to move, right? For example, you can supply heat energy, right? Or you can through some other ways, which we'll talk about later, by introducing impurities, right? By doing so, and then we can create some free carriers. So this kind of material we call semiconductors, which is extremely useful. So then you may ask, for metal, since you have freely movable electrons, so why not just use metal to fabricate the devices? And so I'll explain to you that this is not so easy. So, okay. If you have electrons in vacuum, for example, you don't have so many electrons, right, in vacuum. So it's relatively easy to control it. You know why? Because I just need to, for example, put the two plate here, and then, for example, I'll let this one ground it, right? And then apply voltage to this. So, and so when this V is greater than 0, and I can see that our just greater than 0, this means that I can pull more electrons to here, right? And I have less electrons, somewhere here, right? Because electron negative charge. And then if this is smaller than 0, and then of course I will push electron away. So I have more electrons here, right? And I have less electron here. That means I can control the movement of this, right? So in this case, you can see that the overall movement of electrons, say for example, is in this direction, and then this moment or in this direction, right? And so then you get current, which is in opposite direction, right? So this will be current direction, and then this will be current direction. You can get to have some sort of net current in space. That's how you can form a device, right? The metal is different. The metal means that you have many electrons inside metal. This means that okay, I just maybe use the same. So that's too many, right? Too many electrons inside metal. So and then what happens that so in this case, if you apply, say for example, okay, this is a sorry. So if you have a, for example, you apply positive voltage to this electrode, and then you see what happens that so basically, as I already said, that you will have electron will be attracted to this, right? So it means that this electron will try to move. Remember, you have many. Okay, just look at just look at the one location. So maybe say for example inside this. So initially neutral. So now if this electron is trying to move to this a little bit, then what happens that immediately initially it's neutral. Remember, this is metal. It's not a vacuum. Okay, so electrons are uniform distributed, and immediately this will be a positive charge. and then this will be negative charge. Why? Because the electron will try to move toward this direction. Sorry. Let's see what happened to this. So I need to go back to this again. Right. So I go back to this again. So now, so if again, remember I apply a voltage here equals 0, and this is grounded. So now, if this electron, you have electron which you try to move in this direction immediately, so this will be positive charge, and then this will be negative charge. And then, of course, you will have an electric field, which is in this direction, all right? And then this electric field will try to push this electron back. So this is, so initially this electron try to move this way, and then you push electron back. So, and then this electric field can be extremely strong if your electron density is very, very high. So basically, when your electron try to move a little bit, remember the density is extremely high, right? So that's why if this electron try to move a little bit, and then it will lead to, so it means when n change a little bit, and this will lead to a very large internal electric field. So we call internal, okay? And then this internal electric field will try to bring electron back. This is called screening effect, okay? It's called screening effect. So this screening effect in metal is extremely strong. And then, so the length which electron can move typically is about 0. Something, 0.5 or 0. Maybe 0.1 or 0.2, you know, angstrom that can range. This means that, for example, if this is a metal, and so this is 1 millimeter and copper wire, right? So 1 millimeter, that kind of size. And so 1 millimeter, so 1 millimeter basically is so 10 to the power and of is a millimeter, right? Or 10 to the power -7, sorry, plus 10 to the power 7, you know, angstrom. And then if you change it 0.1 angstrom, so that's why the ratio is 10 to the power 8. So this means that the change is negligible, right? So this means in principle, what does this mean? This means that initially, if you have a 1 milliampere of a current, which is flowing, 1 milliampere of current, sorry, ampere, is flowing in the copper. If you apply a very strong electric field, the change you can cause is this. So basically this, right? So this means that it's negligible. The change is negligible. So this means you cannot cause any cause any change to the electric conduction in the copper. So this is similar, just like a ocean. Okay, so inside ocean you have the water, right? Okay, so now if in the water, if you want to push this water away, right, and it's extremely difficult using whatever means, right? And however, if the ocean is just like a sponge, this means that you have a very little water inside. Of course, it's easy for you to squeeze it, right? So that basically is the intuitive picture which I put here. So you can see that metal is a very good conductor. You have a lot of electrons inside, but you cannot use this one to make devices. This means that you cannot make a switch, for example, you cannot make an amplifier. Why? It's very difficult to control electron movement inside a metal, right? And semiconductor is different. It's just like water inside a sponge. You can squeeze it, right? And you can fill up it very easily. You can also squeeze it out very easily, right? So, and the semiconductor, what's good about this? So you can make it very, very small. That's the reason why now we have all these electronic circuits, right? And inside CPU, you have so many transistors, right, in a very small volume or area. So that's because that you can make a device very, very small. So now we are talking about 3 nanometer to 5 nanometer at the production level, right? So very, very small. Okay, and so if you look at overall development of electronics, you can see that before we had a semiconductor, and then vacuum tubes are very important electronic devices. So we call macro, right? Macro electronic devices because they are very big, right? And then, of course, in 1947, and the first germanium-based germanium semiconductor, right? Germanium-based transistor was invented, and after that, and then people just try to make it as small as possible, and then put more devices on the same chip. So then that's the reason why we are enjoying all these different type of electronic products, right? And so now we are more or less reaching the limit, but not a very fundamental limit. It's basically still at some sort of technology limit, but of course eventually we'll make a fundamental limit, and then we cannot reduce the size further, and that's the reason why people are trying to look at all different new materials or new device concepts, right? And some of them will make use of, say, for example, spin of electrons, because for all these vacuum tubes or semiconductor devices, so basically just look at the charge of electrons. An electron has a spin as well, right? And also in quantum mechanics, we know that right now, so why it's so difficult to control the electrons in semiconductor or in metal? That's because that electrons are moving in all random directions. And then if you find a material, right, you find a material which you can control the movement or moving direction of electrons, and then you have a complete different type of devices. So that's called topological, materials, right? And then people are still trying to find this kind of materials. Although so far we have not, we have some sort of materials, but it's still not perfect, right? So once you can find out this kind of material, and of course, and you don't need to use a superconductor, and then you have the possibility to reduce the resistivity to a very, very low value. And of course, this will reduce the heat and then solve all the problems which current electronics are facing. Okay, so now we look at first we look at how electron will move in free space first, okay, and quantum mechanics. So as I said that in quantum mechanics, and so what I will do that you don't need to specify the position of electrons. You cannot specify anyway, right? So the only thing you can do is to find the wave function. So the wave function will indicate the state of this electron, right? So to find this wave function, and you have solved the Schrodinger equation. And then Schrodinger equation, basically given by this Hamiltonian, and use the Hamiltonian to act on this function. And then if you find a solution which is satisfy this equation, and then that wave function basically is the quantum mechanical coordinate system in a certain sense you have found, right? So once you have this, and then at each state, then you have a different energy, okay? So now the Hamiltonian of a free electron you just only have a kinetic energy term, right? So why this is the case is because that the potential energy for free electrons, you can always specify that the reference is at 0, or means that once you call free means that potential energy is 0, because potential energy is not uniquely defined, right? So you can choose whatever reference you want, but if you call free electron means that the potential energy is 0, and then basically at the vacuum level, and then your Hamiltonian will only have a kinetic energy term, which you can by this one, right? This is a del square, okay? And to solve this, since for hydrogen atom, we use the spherical coordinate system. But for free electron, of course, you don't need to use a spherical coordinate system and there's no spherical symmetry here, right? So that's why the natural choice of coordinate system will be Cartesian coordinate system, X, Y, Z. And then in X, Y, Z coordinate system, to solve this second order differential equation, so we can see second order, right? Second order. And it's obviously use this separation of a variable method. So separation of variable. So what does this mean? This means that you just try to find a solution such that this wave function or solution of this second order differential equation is a product of 3 functions. And then each function is just dependent on a single variable. So that's why I have X, Y, and Z, right? And this is called separation of variable method. And then we substitute this into this Schrodinger equation. So SE stands for Schrodinger equation, okay? And then of course, we have 3 second order differential equations, right? So, well, if you find this difficult to understand, I will try just to explain to you why this is the case. Okay, and if you, in general, if you have a second order differential equation involving a del square, for example, it's phi x, y, z, which is now we just use a different constant, which is given by this one. And then we can use this so-called separation variable method. We can see that this is a function of x, and then y, and then z, right? So now we substitute this in here. So, and then your del square, remember, is given by partial square, partial x square, partial square, partial y square, partial square, partial z square, right? So that's why your del x, this one is substituting here, and then you have a okay. So x, maybe just this bracket. So x, sorry, and y, and then z, that, right? So this is equal to this one. So sorry, the x, and then y, and then z. Okay. So now, so this one we just use this product rule, and then we have partial square x, partial x square, and then we have y, z, plus, and then partial and y square, there's y, and then partial z, sorry, partial y square, and then have x, z, and then plus partial z square, so that. And then we have xy, right? And then epsilon x, y, z. So now we divided both sides by this, and then we should have 1 over x, partial square x, partial x square, plus 1 over y, and then partial y square, plus 1 over z, and partial z square equals epsilon. Okay, so now remember, this is a constant which is independent of x, y, and z. And so this is a function for x only, this function y only, so this function is z only. So this means that the only solution is, so this will be equal to a constant, and this is a constant, and then this is a constant. So all these three constants are not equal, are not dependent on any of the variables. That's the only possibility for you to have a solution, right? Because the three terms, they have different, dependent on different, independent variables. So this means they have three equations. So this one is a constant, which is epsilon 1, this is another constant, and then this is another constant. So that's the reason why there's three second order different equations. So which is anything here, right? So that's why, so one is this one. Okay, so this x, remember initially is 1 over x here, just bring here. That means y is 1 over y, bring here, just now explained it, right? So now I have this is three separate second order different equations. So now the general solution of these three different equations is very easy to find out. So you can see the second order derivative of any function which is proportional to itself. This means the general solution is always like this. You have the exponential function, right? So you can substitute this in and verify. You differentiate this one twice, you will get minus kx squared per here, right? And then you get back this one again. So that minus kx squared basically is this coefficient, right? So similarly, for this one, and then you can get this, and then for this one, so this is a general solution. Okay, so now you put these three together. So, and then you have cosine, remember, is x, right? Multiplied by y, multiplied by z. So a1, a2, a3, multiply, just call it a. And then this exponential ikxx, ikyy, ikz, ikz, z, and then just put together is ik dot r, right? That's what I have. Okay, so I hope you understand this, right? So these three terms plus together is ik dot r, right? And so this basically is a general solution for this Schrodinger equation, right? And then you know this is a wave equation, it's a plane wave, right? So I already explained this in lattice vibration, right? When we talk about lattice vibration, I explained to you why this is called the plane wave. So this is just a plane wave solution. So this means that the free electron wave function, this is a plane wave, okay? Now, so once we know this, and then of course, so you can substitute this in because you differentiate this one twice, right? And then you get EX. So the EX basically is given by, okay, if you substitute this one here, right, you see what you have. And then you have minus h squared 2m. Then you differentiate this one twice, you get ikx squared. And then of course, you get x itself, and then it's given by ex and then x, right? So this x cancels out. So you can see that your ex, and then this I squared get minus 1, right? So that's why I get ex, which is given by h squared, and then kx squared, and then divided by 2n, right? So that basically is this one. And of course, from here, you can get this kx vector, which is given by 2m ex divided by h squared, right? So that basically this one. Okay. So similarly, and you can find out you can find out this ky and then kz, right, from this one to this one, and then you put together. So you have e, which is ekx plus ky, ekz, ky plus ekz is h squared kx squared divided by 2m, right? That because your ex is about this one, the kx squared, and uy ky squared, ez kz squared, right? That's why I put together this one. So this is a very important result we call EK dispersion. So this is what I explained when we talk about in lattice vibration. So you get a phonon, right? So so phonon does not have a mass. So that's why when we talk about the dispersion, we are talking about the omega Q. And then Q basically, electron use K, phonon use Q, they are the same thing. Okay, they are both wave numbers. So Q is a wave number for lattice vibration, and then K is a wave number for electrons. So Q basically is a wave number for phonon, and then K is a wave number for electron, right? So, for what this? For this monatomic chain, right? And then the dispersion, right? We derived. So this is something, this one, the first Brillouin zone, right? And so that's the phonon dispersion, you call omega Q. So once you know the dispersion, you know how lattice vibration behaves inside the specific lattice. And similarly, for electron inside the lattice. So what do we want to know? Because electron is a wave, right? Remember, lattice vibration phonon is also wave. So for wave, we only want to know what's the dispersion. So once we know the dispersion, we will know the behavior of the wave. So that's why now for free electron, and so we find that this dispersion basically has a parabolic shape. So that's given by this one. So E as a function of K, you get from here. So E as a function of K, you get this parabolic dispersion. So this basically determines the property determine the behavior of electrons inside a certain medium. But here we talk about it's a vacuum, it's free space. All right. Okay. Later, anyway, we'll come back to talk about this one again once we have the so-called effective mass concept, right? Okay. So now, and how about the momentum? So for free space, remember the momentum operator is given by this one. I already explained it when I talk about the basic concept of quantum mechanics. And so the moment operator is given by Planck constant divided by I multiplied by del. So it's given by this one in XYZ coordinate system. Okay. So now, if we use this operator in quantum mechanics in general, so you can use any operator. Hamiltonian is the energy operator, right? you can use any operator to operate on this wave function. And then you find this is a constant, multiply with the function itself. And then this alpha basically is the physical quantity, which if you try to measure it, and then the value will be given by alpha. So it means that if O is a momentum operator, and then if you can find phi satisfy this equation, then this alpha basically will be the momentum, and you try to measure it. Okay, and then if this is a Hamiltonian, and the alpha will be the energy, you should try to measure it or observe it, right? So just try to realize that in quantum mechanics, so any particle at any time will be described by a state variable, which is a wave function. Okay, so this wave function, just try to realize that in the sky, you have so many stars, right? And then each star basically may represent a state of that particle, right? And then so mathematically, and then this is defined by a linear combination of an infinite number of base wave functions, right? And then at that state, and then you have a finite energy, and then you have a finite momentum, right? That's what I found out. And in classical physics, and of course, once you know velocity, so velocity multiplied by mass will give you the linear momentum, right? And in quantum mechanics, so how do you find out this? You don't integrate from Newton's second law. You just try to use the this electron. You use the momentum operator. Okay, so mathematically, you just use this operator to operate on this wave function, right? And try to find out the proportional coefficient. So now this is a momentum operator. So we try to use to operate on this wave function. This is a free electron wave function, which we just found out, right? And then remember, and so you have 1, 2, 3. These are the components because momentum is a vector, right? Then just put this in here, here, and here. So basically put in here, right? And then here, and then here, right? So just put in. And then you just try to differentiate this one with respect to x. And so A is a constant, you don't need to differentiate, right? You want to look at this k dot r. So you have kx x, which is the only term which counts as x. So you differentiate this one once with respect to x, you get ikx. So that's one here, right? And then you go back to the function itself, right? And similarly for this one, you differentiate this one with respect to y. You want to have kyy, which is the on y. You differentiate this one, you get coefficient iky. And for this one, you get ikz. Okay. So now this exponential term basically is a wave function itself, is common. So this one, this one, this one, they are the same. So you take it out, and that basically is your wave function. Which one? This one, right? It's this one itself. And then you have a I, cancel with this I. So now inside this bracket, you have kx, ky. So kx, comma, ky, comma, kz. That basically is the k itself, is a vector. That's why I have hk, this one. So now you compare this one, okay? So you compare this with this, and then, so hk, this hk basically is the momentum, right? So that's why we say that the momentum in quantum mechanics is defined by this. It's called hk. So k is a wave vector. So now you can see this k is extremely important, right? It's a wave vector of the wave. At the same time, you multiply by Planck constant, and then you get the momentum of that particle. Okay? And then once you know the k, you can also find this wavelength. So that's called the Broglie wavelength. Basically, it's for any object or any physical object. You can treat this one as a wave, of course, for all the particles. And then by the wavelength, you can capture basically is from the wave vector, right? So of course, when when this k is very small and the lambda very large, k is large and lambda is small, right? They have this kind of relationship. Okay. So now we look at the physical meaning of the EK dispersion, right? We already said that this EK dispersion is extremely important, right? And then that's for electron or for any particle with a mass. And then for a particle or quasi-particle without a mass, and then we use omega k, all right? So why this is important? And we look at the curvature of this. So And so if you have a very simple function, so the function f is a function, f is a function of x, right? And then you can define the curvature of this at any point for this function. So what does this mean? This means that, so if you sketch out this function, then so this x, and then this f. So if this kind of curve, so at any point you have a different curvature. For example, here you have a large curvature, right? And then here you have a large curvature, and here you have a small curvature. So the curvature mathematically can be found from here. So just if you are not familiar with this mathematics, so there's a link here. So you can go back to look at so this link, right? And then this is the second order derivative with respect to this independent variable, which is x. And here you have 1 plus this first order derivative square. And this is the power of 3/2. So that's a curvature. Okay. So now we can apply this to this EK dispersion. So in EK dispersion, so E, so is your F here, and then K is your X, right? X here. Okay. So now the curvature of this EK dispersion curve and at any point and can be written like this. So dE dk squared, that's this second order derivative, right? And dE dk, the first order derivative, right? And then we can find out what this one very easily. So we find out that, so that basically given by this. This second order derivative and this first order derivative. Now we try to find out what happened at k equals 0. So why we're only interested in k equals 0? Because later we know that in electronic band structure, and so we are only interested in electrons as a local minimum. So why we're interested in local minimum? Because electron will try to occupy the local minimum first. Okay, so because electron always try to fill up the states with smaller energy first. So that's why we're only interested in this local minimum. So the local minimum, so basically at the k equals 0, and the k equals 0, the k equals 0, so just substitute this is 0, and then you just get this. And then you find that actually the curvature somehow is related to the mass of the particle. So the mass of the particle is by h squared divided by the curvature. So now in the question, you may ask the question, since now we are talking about the free electrons, right? So electron in free space. And then the mass should be the rest electron mass, right? It's a constant. So why do we need to put it in such a way? So now, of course, now we are only concerned about electrons in free space, and then this is a constant, you're right. And however, and so we are more interested in the situation that when electron is inside different type of a material. So when electrons in different type of material or different type of semiconductor, so later we know that actually the electron mass is different. So this is called effective mass, which is extremely important for understanding the electronic property of semiconductors, right? So to highlight this difference, so this basically is what you will see. So you can see that if, of course, in vacuum, you only have one type of dispersion curve. However, and if you have two different type materials, and then for example, this dispersion is for one material, and then this dispersion is for another material. And then, so what does this dispersion mean? So this dispersion simply means that M1 is smaller than M2. So it means that if you have a material in which electron has this kind of dispersion curve, and then you have another material which doesn't have this kind of dispersion curve, so this means the effective mass of electrons inside the material is different. In other words, and the same driving field, so the electron with a smaller mass can move faster than the electron with a larger mass, right? And then, so how is this compared to the omega Q dispersion for lattice vibration? So for lattice vibration, remember, we are not talking about how fast, what's the effective mass of a phonon, because phonon does not have a mass, right? So, but we use omega Q dispersion to describe the group velocity, of this lattice vibration wave, right? So, and the different dispersion will tell you that the lattice vibration or lattice wave have a different group velocity or phase velocity inside the material, right? So that's what we know. And of course, the momentum will also be different. So because we can always have two pictures, so one is wave and the other is a particle. So once we use a particle picture, and then we have this momentum concept, right? Okay, so next we look at, we just try to move a little bit towards the real situation. This means that we try to use electrostatic potential to basically affect, right, to alternate and the electron moving path, right? Just now we talked about free space. So the first one we call something like a simple rectangular potential barrier, okay? So why do we need to know this? And that's because that in real material, the electron will experience many different type of potential barriers, right? Due to electrostatic potential of other electrons in the nucleus, right? So now suppose we have this very simple rectangular and one-dimensional potential barrier in x direction. And then if you don't have this potential barrier, and of course, when electrons, for example, are propagating from left-hand side, and then they will just move freely to the right-hand side, okay? If you don't apply any electric field. And however, if you have this kind of potential barrier, and what happens that part of electrons will be reflected, right? Because electrons are a wave, okay? And then in classical physics, so if this electron energy is smaller than this energy barrier, and this basically electron will be 100%, it will bounce back. However, in quantum mechanics, and it's completely different. So in quantum mechanics, even this electron energy, right, is smaller than this potential barrier height, and then a certain percentage of electron will be able to tunnel through, okay? And then you have this wave which is propagating towards the right due to the tunneling, right? And how to find out this tunneling probability? And then again, we go back to this Schrodinger equation. So the Schrodinger equation is, so now we have now three regions. So left and the right. And in between, we have this barrier region. So in region 1 and region 3, if we specify that the reference of the potential energy is here, which is 0, and then of course the potential energy in the barrier region will be the barrier height, which is the V0, right? So that's why the Schrodinger equation in general is just given like this. Remember, when we talk about the potential, the Hamiltonian, and this V is part of the Hamiltonian, which is always at the left-hand side, which is plus V, right? So, but you can bring this one over to right-hand side, it becomes minus V here, okay? So this actually is part of the Hamiltonian. See, now this is just constant, so that's why we just bring it over here. We don't need to put this side, right? So now, and then, as I said, in region 1, region 2, region 3, V is 0, and then in the region 2, and then this is V0, which is like this, okay? So now we can solve this Schrodinger equation. So, so in the region 1, basically is x smaller than 0, right? And then we have a right propagating wave. So basically, it's given by this one. This means this part is the wave, plane wave, right? So basically, it's like in free space. It's propagating towards the right. And then we have a reflection. So that's why we change this one to minus sign here, right? And then so the coefficient basically indicates what's the percentage of reflection. So that's why I have both right propagation and then left propagation wave then put together for x smaller than or equal to 0. And then inside this region, and then we have both right propagation and also left propagation. So right propagation means that you tunnel through this interface thing. You continue to go to the right. And then once you reach here, you'll be reflected back again, right? Part of this will be reflected again. That's why you have a left propagating wave as well. But unlike in this case, and then you have a free electron, the plane wave. Inside this, if you're, since the electron energy is smaller than this, then what happens is that you have this decaying wave, So this means that instead of it have a complex phase here, then you have a real phase, right? So this real phase means that so one is positive, the other is negative. So this is for okay, anyway. So if X is positive, so not in this case, right? So in principle, you will only have this one because so this one will be if initially, so if you see this part also decaying, and then you can put together like this. So and then this part anyway, if this is positive, this will be 0, right? Because otherwise this wave will increase. This does not make sense, right? So this part basically you have here is because you can also have wave which is propagating in this direction. But now if you don't have wave propagating in this direction, and then just ignore it. But anyway, in general, you can put here, right? And then, so this part, again, is the free electron wave. So you can see that the electron is propagating to the right. So basically, same like this one, but the coefficient is different, right? And then K is given by this. So that basically is when this is 0. When this is 0, and then this is just like a free electron case, right? So you have this one. And then beta is given by this. That's inside this region, okay? So now, of course, this beta itself is positive, right? So how to get this? And then you just need to put the V naught here, and then you try to solve this one, right? By substitute this in, and then you find out beta basically given by this one. Okay? So now, and after that, we just apply the boundary conditions. So the boundary conditions, we have 2 boundary conditions. So one is that the wave function is continuous, and another one that is the first order derivative, which is continuous. Suppose that, okay, this is quantum mechanics, we'll not go to details. So what I mean, of course, wave function continuous is understandable, right? Because otherwise, the electron has to disappear somewhere, right? And then this first order derivative is continuous means that the flow is continuous. This means that the electron is flowing, and its flow of particles should be continuous, right? So you have these 2 boundary conditions, and then at x equals 0, okay, and then you have 2 equations, and then x equals L, and also you have 2 equations, right? And then 2 equations, and then you have how many unknowns? 5, A, B, C, D, and F, right? So this means that you cannot have specific solutions for all these 5 coefficients unknowns, but you can express 4 of them as a function of the other one, right? By doing so, and then we can, for example, if you express A as a function of F, right? And then you can find a ratio, because they are linearly dependent on each other. And then you find the ratio. So that ratio basically is the tunneling coefficient or transmission coefficient, right? It's just is given like this. Okay. So basically, it's the ratio. So you can see that it's the ratio between this one, right? So this one divided by this one is the amplitude ratio, right? And the probability, tunneling coefficient means that is a probability coefficient. This means they have to square it, right? Remember, how do we calculate the probability density? It means we find the product of this one and the complex conjugate of itself, right? So that's the reason why you have a square. So you square it, and then this is what you have, okay? So 1 divided by this, right? And then, so look at the extreme case. And of course, in general, this will be larger than 1, okay? So when this larger than 1, of course, this tunneling coefficient will not be equal to 1, okay? Unless this term is 1, but this will not be 1, 0 is not 0 anyway. So, and so we look at the extreme case when V naught is infinitely large. When V naught infinitely large, and of course, so you get a V naught square and this is V naught. So eventually, so this will become infinitely large, and just ignore this one, and this will be 0. So it means that when V naught is infinitely large, and then you won't have any tunneling coefficient is 0. Okay. So we look at the general case that when this E is smaller than V naught, so this means that a particle's kinetic energy, so lower than the barrel height. But this beta L is much larger than 1. Okay, look at this case. And then you get this. Okay, so beta L much larger than 1 means that either barrel height is large enough or the barrel width is large enough, and then you have this one. Okay, and then you have this kind of exponential decay. So this means that the Turner coefficient will decrease exponentially with respect to both beta and L. Where beta is related to the remember the V naught is the potential energy barrier, and L basically is the width of the barrier, right? So it's understand. Okay. When E is greater than so this basically is this situation. So E is much more than V naught. It's more than V naught, right? You can see that it decay exponentially, right? And then part of electrons will turn out through, right? Instead of completely reflected back. That's a classical physics. Okay. And then when beta is a complex number, so what does this mean? This means that when energy is, go back to this one, when energy is larger than V naught, right? And this will be a complex number. So this means that kinetic energy is larger than the barrier height. And then the beta, you can, since it's a complex number, you just use alpha, which is a real number, and then just transfer like this. And then you get this. Now, this is very interesting. So what this? So this means that when alpha L is a multiple of pi, and then this will be 0. When this will be 0, and then T is 1. So what's this situation? This basically is called resonant maternity. So this means that when electron move from here to here, right? From here to here, and then the phase, if you gain is a pi, and then you reflect back, and then another pi. So pi and pi give you a 2 pi. So once you have a 2 pi phase difference between forward wave and the reflected wave, and then you have this phase matching condition, and they have resonant maternity, and then this will be 1. This means all the electrons will go through. However, and even when this E is greater than V naught, when you don't satisfy this equation, it means this is not equal to 0. If this is not equal to 0, and then V naught, of course, is finite, since E is greater than V naught in this case. So that's why overall, this is a number which is greater than 0. So this means that the T will be smaller than 1. So what does this mean? This means in quantum mechanics, even this E is greater than V naught, that not mean that electron will go through 100%, turn out or go through without any, influence of the barrier, and it will only not experience the influence of the barrier when you satisfy this phase matching condition, and otherwise, and then electron will be scattered, right? So this means in quantum mechanics, so no matter your energy is smaller than barrier or larger than the barrier, you still have this so-called reflection or scattering effect, right? So that's the difference between classical physics and quantum mechanics. Okay, so that's the barrier. So now, what happens if we flip this barrier into this quantum well? So this means that now I have something like a negative barrier. So this means that I have electron which there's a very small region, right? And then within this small region, the width of the L, and then this is an infinitely deep well, potential well, and then outside well, and then the barrier is infinitely large. So you can define it in 2 ways. One way, you just call this well here potential energy 0, and then outside will be infinite high, which is positive. The other way to define this that outside is 0, and the inside is minus infinite deep, infinite high. But here we use the first definition. This means that in this region, potential energy 0, and then outside in the left and right, and then potential energy infinite high. So in this case, and you have a situation called quantum well, right? It's a quantum well. So in this case, so we can, for example, use again apply a Schrodinger equation to this, and then so you can see that we have this is kinetic energy operator is a part of the Hamiltonian, And then the potential energy part for the Hamiltonian, we just put at the right-hand side. Again, we could do so because this V is a constant, right? Although it's changing in x direction, but it's a constant. That means in the left and the right region is infinite high, is a positive number. And then inside this region is 0. Okay, so that's why it's defined here. So now, of course, outside the barrier, right? And since V is infinite high, you should not have any electrons. Just now I already talked about turning, right? So when V is infinite high, and then you cannot turn us through. This means that there's no electron inside this barrier, also inside this barrier, right? And so, but inside the quantum well, and then we can apply this Schrödinger equation. So now you can see that since our this quantum well or confinement, this is called quantum confinement. So the quantum confinement is only in x direction. This means that the electrons confined in x direction, but electrons can move freely in y and z direction. Okay, so this is called quantum well. All right. So, and then of course, if you can move freely in y and z direction, and then electron wave function should be given as this plane wave, right? So the ky and the kx, it's just free electrons which can move freely in y and z direction. But in x direction, and then you have this confinement effect. So now, and since electron cannot move in x direction and into this barrier region, and then since the electron will be confined, it will be 100% reflected back from a right boundary, 100% reflected back from a left boundary. So eventually, you can only have this kind of a standing wave. Okay? Any other wave you can try to sub in is cannot be sustained by this kind of potential environment. So you only have this one. Okay. So once you have this now, and you substitute the boundary condition in, this means that this wave function should be 0. And so here and also here, right? Now, so at x equals 0, and then this must be x equals 0, this must be 0, and x equals L, this must be 0, right? So this means that so A must be 0. Okay, you go back to this. So when x is 0, this means this is 0. When x is 0, sorry, this one. When x is 0, this means that this is 0, right? Because x sine 0, 0. And then you only have this term. So since this is 0, x is 0, this means A must be 0. Okay? So it means they have this one. So, right? So when x is 0, and A must be 0. And then you only have this another term, which is when, okay, maybe I just write down this one first. It's the easiest way to understand, right? So remember the phi. So phi is cosine, sorry, use cosine, okay. It's A cosine kx x plus b sine ky, sorry, kx and then x, right? So this means initially, so when x is 0, so this term is 0. So when x is 0 means that this term is 0. So when this is 0, and then of course since this is 0, A must be 0. So it means you don't have A anymore. So from this one, and then next, since A is already 0, you only have this term, right? So you put the L here. So kxl, so this must be equal to 0. So that's due to this one. So when this is 0, so you cannot let B be 0, right? If B is 0, since A is already 0, B is 0, and then this is called a trivial solution. So you want a non-trivial solution, meaningful solution, and then you require this sign to be 0. So sine kxl to be 0. So this means that kxl equals n pi, and this is integer, right? And then from here you can find that this kx actually quantized. Okay, so since nx is integer, and then the energy in this case begin by this term, since we have this y and z direction, and you can move freely. So that's why So this part of K we call parallel, which is not quantized, and only the moment in X direction is quantized. Okay, so this is a K parallel. So eventually, so you can see that we have this kind of picture. This means that due to this quantum confinement, right? And then what happens that and so energy become quantized. So that's because that this part, the moment in X direction is confined. Okay, and however the parallel part is still the same. It's not quantized. So it means they look at the EK dispersion, and for the first quantized level, so you still have this parabolic dispersion with respect to K parallel. So that's because that the electron can still move freely in Y, K1, and Kz direction. And then after that, you have E2. So this is due to the quantization in X direction. And you still have this parabolic dispersion, but now you can see that this minimum energy is different from this one. So that's because your N now is Nx over 2, right? But this is 1. Okay, and similarly, and after that, you have E3. So you have this kind of dispersion. It means that in principle, for quantum well, in the direction which is parallel to the well, and you still have this parabolic dispersion because the electron can move freely. But perpendicular to the well, the energy is quantized. Okay, so that's the conclusion we have often for this. Okay, so now we can try to calculate what's the quantized energy levels in the X direction. So this is what we just derived. And so now, in order to deal with the situation in real material, we just try to change this M into M star, which is the effective mass. And so multiplied by, so effective mass, there's no dimension, dimensionless. It's just a number. Multiplied by the free electron mass. So free electron mass, is a constant. It's a fundamental physical constant. So that's why whatever electron mass you have, you can express this one as a product of a dimensionless number, which is called effective mass, multiplied by the free electron mass. Okay, so we do this. And then H is Planck constant, which is a fundamental constant, we just put in, and then we get this kind of very interesting results. So it's 0.377 and 1 over M star. M star is typically less than 1 or roughly 1. Or, for example, if it's 0.1 times this one, then it's just 0.1, and no dimension. Okay, and of course, Nx is an integer, and L square, L is the width of the well. Okay, so this is what we have obtained. Now, and the next concept we call normalization of wave function, because and the wave function just now eventually we derive it. We only have this term, right, in the X direction, and then we can try to normalize this. So once we normalize this, and then we just integrate this one from 0 to A, right? So the SK 0 to L, 0 to L. Okay, not A. Okay, 0 to L. Oops. I need to come back to this one. So we integrate this one to L and then normalize it, and then you get the Pn, which is this one. You just put here. So now, we have wave function. So this is for the first one, and then this for the second one, and this for the third one. And remember, you still have the plane wave that's in X, Y, and YZ direction. You can normalize this one as well. So that's why, since we are only interested in the wave function inside this region and along the X direction, that's why I try to normalize this. And then you can see that this is the wave function, right, for n equals 1, which is given by this one. Let me turn on this pointer, right? And then you can see this is just half of the sine wave. And then n equals 2, that's the full sine wave. And then, so n equals 3 is 1.5, right? So you can see that the energy will increase linearly with the number of zero crossing of the wave function inside this region, right? So you can see this one, there's no zero crossing except for the two boundaries. And then this you have 1, and this you have 2. When you move on further, you have 3 and 4, and just continue, right? So that's basically just tell you roughly the idea in quantum mechanics. And then if you have a states which is represented by wave function, which vary rapidly in real space, and then typically that states will have higher energy, right? Okay. If you have a finite well, and then what happens that this is quite complicated, okay? If you have a finite quantum well, and then you can see that this V naught will not be infinitely large, right? It's just a finite number. So in this case, and then so this will be the potential function, right? So this is a outside the well, and then this is inside the well. Okay, so and then of course you still can solve this Schrodinger equation. I think we just have a break here first, and then after that I come back to this finite quantum well.